In this video, we're going to take a look at titration and buffers. Neutralization happens when an acid and a base are combined together, and the product is always water and a salt. So the acid and the base are neutralizing each other. The H plus ions are being neutralized by the OH minus ions of the base, resulting in, again, just water and a salt. So the most common one is hydrochloric acid with sodium hydroxide. So one of the strongest acids with one of the strongest bases, completely neutralizing to make salt water. This neutralization process is used in what we call titration, by taking a known concentration of an acid or a base to then neutralize an acid or a base with that known concentration to determine the concentration of your unknown one. So solution known concentration is called either the standard solution or the titrant. And if you take a known amount of your unknown concentration solution and slowly add in this titrant until an equivalence point is reached, you can then use that neutralization process in stoichiometry to determine what is the concentration of your unknown substance. So when you do titration, you use an indicator to let you know when you reach the end point, which is usually phenolphthalein, because phenolphthalein will go from clear when it's an acid or a neutral solution to when it becomes a base. And we know that the equivalence point is going to be really close to when it changes from neutral to basic, because when you're adding in your titrant, it has very quick changes of pH when you get around that neutralization point. So it's going to be close enough that we can just call it the same. And then again, using stoichiometry and then our molarity equation, you can figure out how many moles of your titrant you used to determine how many moles were in your unknown solution, and use that volume of your unknown solution to then determine the molarity of your unknown solution. So let's take a look at how we'd go through a titration in this entire process. So you have a burette and an Erlenmeyer flask. The burette is going to contain your known or your standard solution that you're going to use as your titrant, and the Erlenmeyer flask will have your unknown solution. So let's say we put 20 milliliters of our unknown solution into our Erlenmeyer flask, and then we'll fill up our burette with our known solution. We'll add some phenolphthalein into our unknown solution again to change color when we get to our endpoint. And then you're going to quickly add in some of your titrant until you start seeing some pink liquid start when it hits the surface. So when that titrant is hitting your unknown solution and you're seeing some pink, you know, well, right there, when it quickly goes in, it's starting to become basic, and that tells us we're getting kind of close. At which point you would slowly add in dropwise, stirring and swirling your liquid until the entire solution goes pink. And now that entire solution is pink, so it tells us it's moved from acidic to neutral to now just into basic, and that is going to be our end point. So from there we can use the amount of titrant, and so if we started with a volume of 0 to a volume of 10, we take the difference. We find we use 10 milliliters in this particular case here. The burette does have graduations on it, so you don't have to actually measure the amount. The burette does the measuring for you. And so now I can use my molarity equation. If I know the molarity of my known solution, molarity of my titrant, and I know how much of it now I used, I can solve for moles of solute, multiply both sides by volume. I find that the moles of solute is the molarity times the volume at which I used. So I can take the 0.1 molar solution that I used to titrate with, and the fact that I used 10 milliliters or 0.01 liters, and I find that there was 0.001 moles of hydrochloric acid that was used here. I can now take that number of moles with my unknown solution. Well, if that amount of moles were to neutralize, then therefore that amount of moles must have been inside my unknown solution. And then using the volume, that 20 milliliters that we originally put in there, I can now solve for molarity and find, well, if 0.001 moles were in my unknown solution and its volume was 20 milliliters or 0.02 liters, I find the molarity to be 0.05 molar. Another way in which you can do this is looking at the titration curve. The titration curve shows the pH as more titrate is added in. The stronger the acid or the base, the more steep this curve ends up being, because a strong acid is going to completely dissociate, or a strong base also completely dissociate. So you get really low or high amounts of pH. And then as it's being neutralized, you're not adding in more H pluses, and or OH minuses, and therefore they're going to be completely neutralized. You can have this really quick change as it is being neutralized around the endpoint. However, weak acids, since they only partially dissociate, you don't have as drastic a change in the pH. It doesn't start as high or as low in the pH. And as you do more neutralizations, you are going to get more particles that are going to be dissociated and put into solution. So it's going to make that happen much more slowly of a process, much more flat of a curve. And then the equivalence point ends up not being right at 7, as we would see with the strong acid and strong base, as they are completely ionized and completely neutralized, because you have conjugate acids and bases that are being formed that are going to also affect the pH. So let's first take a look at some different acids and how their titration curve looks. So first we have here hydrochloric acid, and hydrochloric acid, as it is being titrated with sodium hydroxide, making water and sodium chloride, is going to make, again, this really flat curve starting really low with a really low pH and a very steep point as it gets neutralized, again, because you have all the H pluses being completely neutralized by all the OH minuses, and then all of a sudden there are no H pluses left, and all you have are the hydroxide ions from the sodium hydroxide, and you get a really big jump. Next one we're going to look at is acetic acid or vinegar. We're still going to titrate that with sodium hydroxide. So a much weaker acid. We don't have as low a pH to start at. We do get a quick jump to start, and then we see how it really kind of flattens out and gradually then kind of increases. And somewhere around 8 is where we're going to get our equivalence point here, again, because that sodium acetate that's being formed, that conjugate base, is going to actually raise the pH as this neutralization happens. And then lastly, let's take a look at hydrocyanic acid, a very weak acid. We start with an even higher pH, just barely into the acidic range there, just about 6. Again, we get that quick jump to the start. And actually, even though we have the hydrocyanic acid still in there, it hasn't all been completely neutralized. The pH actually moves into a basic pH above 7. And our endpoint, again, is going to reach to that 50 milliliter point. So we have a pH of close to 10 when this finally becomes completely neutralized, again, because of the sodium cyanide that's being formed, the conjugate base that's formed as this titration is happening. So we see with the Kas, the strength of these acids, again, hydrochloric acid, really strong acid, Ka of 6.2 times 10 to the 6th. As the Ka decreases, again, you have higher and higher point for your curves will start, and a higher and higher pH actually where they get neutralized, and it becomes flatter and flatter. So these are each monoprotic acids, but let's take a look at what a diprotic would look like. So we'll go backwards in this case. We're going to start with our sodium carbonate. It's going to be very basic. We're going to titrate in hydrochloric acid to make our carbonic acid and salt. So we're going to start at the high pH, and then as the hydrochloric acid is going to neutralize the carbonate ion to hydrogen carbonate, which is a -1 charge, we see our first steep point, our first equivalence point. And until all of the carbonate ions are neutralized, we'll then move on to the second stage of this titration. And again, we get a second equivalence point here. So we actually get 2 waves in this titration curve here, because we have to add 2 hydrogens to each carbonate ion to get to our carbonic acid. So we can actually use this, though, as a really important aspect in chemistry, is called a buffer. When we have a solution that as acid or base is added, it causes very small changes in the pH. And again, thinking back to our weak acids, that slide a few ago, it stayed pretty constant across till we got to that neutralization point, to our end point of that titration. And that's because as you're adding acids or bases, they're able to be neutralized, and you have these weak conjugate acid-base pairs that allow this very slow change in pH to happen. So if you combine a weak acid or a weak base with a conjugate salt, you get this equilibrium balance, and again, adding acid and base neutralizes, creates more weak acid or weak base, and causing a pH to have a very small range when it changes as these are being added. Again, they can neutralize both an acid and a base. It doesn't matter. They don't work for just one or the other. They're able to neutralize both hydrogen ions and hydroxide ions, again, as they're in equilibrium. So the range at which these happen is dependent upon the dissociation constant and the concentration of the acid or base that you put into your buffer, and also the concentration of its conjugate on the other side of its equilibrium equation. So the buffer capacity, though, is the amount when eventually you can no longer add any more acid or base and not have a jump in the pH. Once all of the conjugate acid or base on either side of the reaction, depending on what is being added in, has been completely neutralized, and there's no more in which it can absorb, and then you do get that big jump, again, like just we saw in our titration curve there. So this is really important in our blood, because we need to keep our blood in this very small range, 7.35 to 7.45. Going below or above that in our blood is very toxic to our body. So there are two different buffer systems in our blood that allow that to happen.